Now we're in 15.2. Looking back to 15.1 for a second, we talked about how to do double integrals over rectangular regions. So we interpreted that to be if f of xy is positive, the surface that you get from graphing f of xy has a volume that we can associate as the set of points between that surface and the xy plane or some region within the xy plane. And for the purposes of 15.1, the regions in the xy plane that we looked at were all rectangles. Those are the easiest cases to deal with. But there's no reason why we can't consider other types of regions in the xy plane that we want to integrate over. So in 15.2, we look at much more general regions. So to illustrate, suppose we have in the xy plane this little region here, D, and we want to integrate some function f of xy over this region. Well, the technique that we developed in 15.1, like we said, only tells us what to do if that region is a rectangle. And so what we do is we expand this function f of xy by taking the region that we want to integrate over and enclosing it in a rectangle. The rectangle we're going to call R, and the region that we care about is going to be called D. And then what we do is we define capital F of xy as a piecewise function, where capital F of xy is equal to just regular f of xy whenever the point xy lies within that region D. And then we define it to equal 0 if xy is some point that's outside of D but in that blue rectangle R. So what that means is the integral of that function f of xy, the double integral, can be taken over a rectangle, this rectangle R, which we have a technique for. But for any of the points, for any of the part of that region R that's outside of D, that integral is just going to come out to 0. We're taking the double integral of 0. So all of the stuff outside of D but inside of R is going to be negligible. And so the double integral over R, capital F, comes out to be the exact same thing as the double integral of D, or over D, of lowercase f, the one that we care about. This kind of illustrates what's happening in 3 dimensions. So again, what we want is this part of the surface that lies above this plane region D. We want to integrate the function giving us this surface over just that region, but instead we enclose D in a blue rectangle and define the value of a new function, capital F of x, to be 0 anywhere else. So the blue here indicates that all of the points on capital F of x are in the xy plane because capital F of x, y is equal to 0. That means it contributes nothing additional to the volume under that surface. Okay, now in practice, what this really does for us is it gives us kind of a theoretical basis for which we can do these types of integrals. But in practice, we don't actually graph a region out, enclose it in some rectangle, and then create this brand new function. This just gives us a way, or a way of knowing that we can integrate functions over general regions. The technique for doing it is a little bit more specific. A little bit more specific to the type of region that we're looking at. So in this section, when we're talking about general regions, we're actually going to be looking at 2 different types of regions. The first we just call a type 1 region. And what we mean by a type 1 region is we're looking at a region in the xy plane that's bounded above and below by 2 functions of x. So y is a function of x in these 2 cases. And then the x values are bounded by an interval on the x-axis. So that's what this set D in set builder notation is describing. It's a set of all x, y, such that x is somewhere between a and b, and y depends on this x here. It lies between the 2 functions, giving us these 2 curves here. Okay, and you can see some different cases here where, of what these regions can look like. In this case here, for example, the two curves, y equals g1 and g2, meet at these endpoints but they don't have to. Notice in this case, we can actually think of this as just one curve, but if we want to think of it as a function of x, we have to break it into a top portion and a bottom portion. Here we just have two curves that have no intersection in that region, but we can still talk about that region for the purpose of integration. So how do we deal with taking a double integral over a type 1 region, assuming that we know what these functions look like, giving us these curves? So let's look at that next. Okay. So remember, when we're talking about iterated integrals for evaluating double integrals, there's that inside integral and that outside integral. And that inside integral, based on what we talked about in 15.1, actually represents the area under a curve. It's a curve that we get from taking the intersection of a surface with a plane parallel to one of our coordinate planes. In this case, if this is my region D here that I want to integrate over, and we've enclosed it in this rectangle here, I want to consider the surface, which we can't see here, but the surface that would be lying above this region D, if I sliced it with this plane passing through x, perpendicular to the x-axis, and passing through this point x right here, okay? So at that particular value that we're using, this interval is bounded by these two functions. So for the specific x value, the interval in D is given by g1 of x and g2 of x, lower bound and upper bound right here. So really, when we're doing an iterated integral, that innermost integral, which represents the area under the curve of intersection between the surface and this plane, would only be integrated on this interval. Because even though we can integrate it from C to D, remember, outside of this region, we're defining that to just be 0. So integrating from C to D, nothing is contributed by the parts of this interval that are outside of that region D. And so for that purpose, we can kind of just think of the integration as taking place over this smaller interval right here, from g1 of x to g2 of x. What that does is change the way that we represent this iterated integral here. So again, here's the innermost integral that I was talking about, the integral of f of xy dy. And notice the limits of integration now, they don't look like constants anymore. They look like functions of x. So what we do is we integrate this function with respect to y, but use the functions of x that bound this surface on the top and on the bottom as our limits of integration. And then the outer limits of integration, a, b, correspond to the interval on the x-axis that we're taking these cross-sections on. So those will be constants. Okay? So when we're doing double integrals over general regions, this innermost integral here will look, for a type 1 region anyways, will look like functions of x, and the outermost interval will look like constants. That's for type 1 regions. Type 2 regions are sort of the counterpart of that. So a type 2 region is a region that's bounded by two functions of y instead of two functions of x. As a set, we can denote that this way. So in this case, it's kind of the reverse of what we saw in type 1 region. Y is on a fixed interval, but x is bounded by two functions of y now. And we can go through a similar argument to show that that double integral can be evaluated this way. Notice this time I'm integrating with respect to x first, and the bounds look like, or the limits of integration look like functions of y. Then once I do that, I follow that up by integrating with respect to y, but that's on a fixed interval. Notice in these cases, whether it's a type 1 or a type 2 region, you don't get to choose your order of integration anymore, unless you want to turn your type 1 region into a type 2 region somehow. For a type 1 region, though, you always integrate with respect to y first. For a type 2 region, you always integrate with respect to x first. Okay. All right. And I'm going to save this for the next video.